What if the entire universe could be described by a single equation? An equation so powerful it could predict the invisible, the dance of electrons, the shimmer of light, the structure of everything that exists. This is Schrödinger's equation. It's not just mathematics, it's the language of quantum reality. Today, we journey through the mind of Erwin Schrödinger and into the equation that forever changed the way we see existence itself. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. The early 1900s. Physics stood at a crossroads. Newton's clockwork universe had been shattered by discoveries that didn't obey its rules. Light behaved as both a wave and a particle. Electrons refused to follow predictable paths. Atoms emitted discrete packets of energy, quanta, Planck, Einstein, Bohr. Each had added pieces to the puzzle. But there was no unifying picture, no mathematical framework that could describe this strange new world. Then came a quiet Austrian physicist with a cat, a thought experiment, and a dream. Erwin Schrödinger was not a man chasing fame. He was a thinker, poetic, philosophical, and fascinated by life itself. In the winter of 1925, he retreated to the Swiss Alps, carrying with him a copy of Louis de Broglie's doctoral thesis, a bold proposal that matter, like light, might have wave-like properties. That single idea lit a spark. If particles have waves, then there must be a wave equation, a mathematical description of how these matter waves move and evolve. And so, by early 1926, Schrödinger derived it, an elegant second-order differential equation that would become the cornerstone of quantum mechanics. At its core, the Schrödinger equation looks simple. H hat psi equals IH bar partial psi over partial t. But behind this compact expression lies the structure of quantum reality. H hat represents the Hamiltonian, the total energy of the system. Psi is the wave function, a complex mathematical object that encodes all possible information about a quantum system. H bar is Planck's constant divided by 2 pi, the fundamental quantum of action. I is the imaginary unit, reflecting that this world operates in probabilities, not certainties. This equation tells us how psi changes over time, how the quantum wave of a particle evolves. But what does psi actually mean? At first, Schrödinger thought psi represented a physical wave, like ripples in an ocean of energy. But when physicist Max Born examined it, he realized something far deeper. Psi itself wasn't directly observable. Instead, its square magnitude, psi squared, represented the probability of finding a particle in a given place at a given time. This changed everything. Reality, it seemed, was not definite. It was a probability field. Electrons didn't have a fixed position until measured. They could be anywhere. And only when we looked did the wave collapse into a single outcome. The universe, once seen as mechanical, was now statistical, uncertain, and profoundly mysterious. Let's see the power of this equation in motion. When applied to the hydrogen atom, Schrödinger's equation perfectly predicted the discrete energy levels observed in atomic spectra, the same spectral lines that had puzzled scientists for decades. It explained why electrons could only exist in certain orbits, and why atoms emitted specific wavelengths of light. For the first time, quantum mechanics wasn't just a set of observations. It was a predictive mathematical framework. This single equation could describe electrons and atoms, the structure of molecules, and even the behavior of semiconductors, the foundation of modern technology. But with great power came great paradox. To illustrate the absurd implications of quantum superposition, Schrödinger proposed a thought experiment, a cat sealed in a box with a radioactive atom, a detector, and a vial of poison. According to quantum mechanics, until the box is opened, the atom exists in a superposition, both decayed and not decayed. which means the cat, too, is both alive and dead at the same time. This was not meant to confuse. It was meant to reveal the strangeness of applying quantum principles to the macroscopic world. Schrödinger's equation didn't just revolutionize physics, it ignited philosophical warfare. Einstein famously resisted it. God does not play dice, he said, unwilling to accept randomness as fundamental. Bohr, on the other hand, embraced the probabilistic nature of reality, declaring that observation defines existence. Schrödinger himself was torn. He admired the equation's beauty, but doubted that it told the whole story of reality. Could consciousness be the key to collapsing the wave function? Or is the universe itself a grand quantum system, constantly observing itself? Questions that remain unanswered, even today. Despite the debates, Schrödinger's equation remains one of the most successful laws in all of science. From lasers to quantum computers, from chemical reactions to nuclear fusion, everything built on quantum principles traces back to this one equation. It's the blueprint for predicting the behavior of matter and energy at the smallest scales. It tells us that reality isn't fixed. It evolves according to probabilities guided by a wave of possibilities. Today, physicists use the Schrödinger equation not only to study particles, but to probe the mysteries of quantum entanglement and quantum computing. In quantum chemistry, it maps the complex electron clouds that define molecular behavior. In solid-state physics, it underpins the operation of transistors and LEDs. In cosmology, it even appears in equations describing the quantum state of the universe itself. Every simulation, every model of atomic-scale behavior, all begin here. The humble sigh, whispering the secrets of existence. When you look around, you see solidity, walls, air, light. But at the quantum level, everything is fluid, dynamic, uncertain. The Schrödinger equation tells us that this uncertainty is not a flaw. It's the fabric of reality itself, a cosmic dance between probability and observation. To understand it is to glimpse the true nature of existence, a universe not made of matter, but of waves of possibility. Erwin Schrödinger may not have set out to redefine the universe, but in doing so, he gave us the equation that animates it. It's the heartbeat of quantum mechanics, the pulse of probability, and the bridge between what we see and what truly is. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about Schrödinger's thought experiment and how his mathematics navigates our modern world. Join me next time for another deep dive into the strange and unusual world of quantum physics.